The speed limit of reality. Something strange happens when light travels. Not a little strange. Not physics textbook strange. But universe rewriting strange. Because when light moves, the entire structure of reality bends around it. Time slows. Length shrinks. Simultaneity breaks. And the strangest part is this: from light's own perspective, none of it happens at all. Richard Feynman once said, "Nature's imagination is so much greater than man's." And nowhere is that more obvious than when you try to understand what light is actually doing when it travels. We grow up thinking motion is simple. A car moves down a road. A plane crosses the sky. You throw a ball, it travels through the air. Speed is just distance divided by time. Straightforward. But light refuses to behave like anything else in the universe. Light always moves at exactly the same speed. Not almost the same. Not approximately. Exactly. Around 299,792,458 meters per second in vacuum. And here's the disturbing part. It moves that fast no matter who measures it. If you run toward a car moving at 50 kilometers per hour, you measure the car moving slower relative to you. If you run away, it appears faster. That's how velocity works. That's common sense. But light breaks that common sense. If you chase a beam of light at 99% the speed of light, you still measure it moving away from you at the speed of light. Not slower. Not adjusted. The same. Feynman emphasized this over and over in his lectures. The speed of light is not just another speed. It is built into the structure of spacetime itself. It is not something light does. It is something the universe enforces. But how can that be? For light speed to remain constant for everyone, something else has to give. And what gives is time. And space. Imagine two observers. One standing still beside a railway track. Another riding on a train moving near light speed. A flash of light goes off in the middle of the train. To the observer inside the train, the light travels equally toward both ends. But to the observer outside, things look different. Because the train is moving, the light chasing the front of the train must work harder to catch it, while the light traveling toward the back meets it sooner. And yet, both observers will still measure light moving at the same speed. How is this possible? Because time inside the train slows down. This is not a trick of perception. Not measurement error. Time literally ticks slower for the moving observer. Their clocks fall behind. Their seconds stretch. This effect is called time dilation. And it is not theory anymore. Atomic clocks flown on airplanes come back slightly out of sync with those left on Earth. GPS satellites must constantly correct for these differences or your phone would give wrong directions within minutes. Light forces reality to stretch in order to protect its speed. But that's only half of it. If time slows, space must also adjust. Objects moving near light speed shrink in the direction of motion. This is called length contraction. From the outside observer's perspective, the moving train becomes physically shorter. Time stretches. Space compresses. All so that light remains stubbornly consistent. Feynman described relativity not as a bizarre anomaly, but as the inevitable consequence of accepting a simple experimental fact. Light speed is invariant. But here is where things turn stranger. Let's attempt something impossible. Imagine riding along with a photon. Imagine moving at exactly the speed of light.
Einstein's equations tell us something shocking. As you approach light speed, time slows more and more. At exactly light speed, time stops entirely. From the photon's perspective, if such a perspective even makes sense, there is no time between emission and absorption. A photon emitted from a star 10 billion light years away experiences zero travel time. For it, emission and absorption are the same event. The photon does not experience distance. It does not experience duration. The universe between source and destination collapses into nothing. This idea is nearly impossible to visualize. A beam leaving a distant galaxy billions of years ago and striking your retina tonight, and for the light itself, that journey had no length and no time. If this is true, then light does not travel through space in the way we imagine. Instead, space-time rearranges itself depending on the observer. Feynman often warns students not to rely too much on mental pictures in quantum and relativistic physics. Do not keep saying to yourself, he said, if I could only imagine how it works. You are not obligated to imagine it. And yet we try.
We copy.
Because something feels deeply unsettling, we think time is universal, a ticking cosmic clock. But light tells us that the rate at which time flows depends on motion. There is no single now across the universe. Two lightning bolts strike both ends of a moving train simultaneously from the ground observer's view. But for the observer on the train, one strikes before the other. Events that are simultaneous for one observer are not simultaneous for another. Simultaneity is not absolute. The present is not universal. Light breaks the idea of a shared moment. This effect has profound implications. It means that when you look at the night sky, you are not seeing objects as they are now. You are seeing them as they were. The moon appears as it was 1.3 seconds ago. The sun about 8 minutes ago. The nearest star over 4 years ago. Distant galaxies millions or billions of years ago. You never see the universe in the present tense. Because light takes time to reach you. And yet from light's perspective, it never takes time at all. This contradiction forces a new way of thinking. Space and time are not fixed backgrounds where events unfold. They are dynamic participants, interwoven into a four-dimensional fabric called space-time. When something moves slowly, space-time barely distorts. But when something moves close to light speed, that fabric twists and stretches dramatically. The closer you move toward light speed, the harder it becomes to accelerate further. Your mass effectively increases. More precisely, your energy increases according to E sends. More precisely, your energy increases according to E sends. That equation's simple, compact, hides the secret. It says mass is frozen energy, and light, having no rest mass, exists as pure energy. Unlike every other object, light does not need to accelerate to reach its speed. It simply is at that speed, always. But here's a deeper question. Why is there a speed limit at all? Why should the universe have a maximum speed? Feynman hinted that this speed limit is not arbitrary. It arises naturally from the geometry of space-time. Think of space-time as having a structure similar to a grid. The speed of light represents the slope of lines that preserve cause and effect. It defines what events can influence other events. If signals could travel faster than light, causality would collapse. You could, in theory, send information backward in time. Effects could precede causes. Centuries ago.
The universe prevents that.
Light speed is not about light. It is about preserving order. It is the boundary between possible and impossible connection. Every event in the universe has a light cone. Inside that cone are all events that can influence it or be influenced by it. Outside the cone lies a region, forever inaccessible. Even now, as you read this, there are parts of the universe that can never affect you. Not because they are too far in space, but because light emitted from them will never reach us due to cosmic expansion. Light defines the observable universe. But this only explains how space-time bends around light. It does not yet explain what light actually is. Is it a wave? Is it a particle? The answer, strangely, is both, and neither. In classical physics, light was a wave of electromagnetic energy. In quantum physics, It behaves like discrete packets called photons. Feynman approached this duality differently. Instead of asking whether light is a wave or a particle, he asked what it does. In his theory of quantum electrodynamics, he described light as something that explores all possible paths between 2 points. When a photon travels from point A to point B, it does not take a single straight line. It samples every possible trajectory, straight, curved, wildly looping, all at once. Each path contributes a tiny amplitude. When you add them together, most cancel out. Only the path of least action survives with significant probability. Light appears to travel in a straight line, not because it chooses to, but because all other possibilities cancel themselves out.
This is not metaphor. It is the mathematical core of quantum theory.
The strange behavior of reflection, refraction, interference all emerge from this principle. When light enters glass and slows down, it is not because it physically struggles through a dense medium like a bullet through water. Instead, photons interact with electrons in the material, creating delays that collectively reduce the effective speed. But even in matter, the fundamental speed between interactions remains c, always c. The universe does not allow light to slow in transit, it only creates pauses along the way. Feynman diagrams visualize these interactions as lines splitting and rejoining particles, exchanging photons, forces, mediated by light itself. Electricity is photon. Magnetism is photon. The forces holding atoms together are carried by light. So when light travels, it is not merely moving through the universe. It is holding the universe together. This realization turns the question upside down. Something strange happens when light travels, but perhaps something even stranger is happening when it doesn't. Because light is woven into the laws of causality, the structure of energy, the geometry of space-time, and the behavior of every charged particle.
It is less a traveler, more a rule.
And we have only begun to understand the consequences.
In the next part, we will dive deeper into Feynman's quantum explanation, where light does not merely bend time, but seems to defy classical logic entirely. We will explore how photons interfere with themselves, how probability becomes reality, and why the act of measurement changes what light does.
Because when light travels, it does not just cross space.
What space even means when light refuses to choose.
In part one, we followed light into relativity, where time stretches and space shrinks just to keep its speed constant. But that was only the surface level strangeness. Beneath relativity lies something even more disturbing. Because when light is examined closely, when we stop asking how fast it moves and instead ask how it moves, reality begins to dissolve. Richard Feynman warned that if you think you understand quantum mechanics, you don't. And nowhere is that more obvious than in the behavior of light in the famous double-slit experiment. Imagine firing photons one at a time toward a barrier with 2 narrow slits. Behind the barrier sits a screen to record where each photon lands. Classical thinking gives 2 logical possibilities. Either the photon goes through the left slit or it goes through the right slit. Particles behave this way. They choose a path. But when the experiment is performed, something impossible happens. Even when photons are sent one at a time, with enough spacing that no photon can interact with another, the pattern on the screen is not 2 bands behind the slits. Instead, it forms an interference pattern, bright and dark stripes, a wave pattern. A single photon somehow behaves like it passed through both slits and interfered with itself. Not metaphorically, mathematically. If you try to detect which slit the photon actually went through, the interference pattern disappears. The act of measuring forces the photon to behave like a classical particle. But if you do not observe it, the photon behaves like a wave, spreading through both openings at once. This is not because measuring physically kicks the photon off course in some crude mechanical way. Experiments have been designed so delicately that disturbance can be ruled out. The loss of interference is tied not to physical jostling but to information. If which path information exists, interference vanishes. Reality depends on what can be known. Feynman called this experiment the only mystery, because everything strange about quantum physics flows from its psyche. How can a photon explore two paths at once? Feynman proposed something even more radical. He suggested that light does not choose a path. Instead, it takes every possible path simultaneously. From the point of emission to the point of detection, the photon contributes an amplitude for every conceivable route. Straight lines, curved paths, zigzags, loops, even trajectories that wander wildly before arriving. Each path has a phase associated with it, like a rotating arrow in the complex plane. When you add all these arrows together, most cancel out through destructive interference. Only those near the path of stationary action, roughly the classical straight line path, reinforce each other. The result? The photon appears to travel a single sensible trajectory, but beneath that appearance lies a swarm of possibilities. This sum over histories is not philosophical speculation. It is the mathematical engine of quantum electrodynamics, one of the most accurate theories ever constructed. Its predictions match experiments to astonishing precision. So when light moves from point A to point B, the universe is not computing a single route. It is adding up an infinity of possibilities. This changes how we think about cause and effect. In classical physics, cause produces effect through a defined chain of events. In Feynman's formulation, events are weighted combinations of possibilities. The photon does not have a history until it is detected. The detection event retroactively defines which amplitudes matter. But that does not mean the photon decides at the last moment. Decision is a human word. The mathematics simply refuses to assign a definite path until measurement. Why should measurement matter? Because in quantum mechanics, measurement is not passive observation. It is interaction. To detect a photon's path, you must couple it to another system, a detector, an atom, a sensor. That interaction entangles the photon with its environment. Entanglement spreads information into the surrounding. And when information spreads, interference disappears. This is called decoherence. The photon's many possible paths do not vanish. They lose the ability to combine coherently. The delicate phase relationships that created interference become scrambled. The world becomes classical not because quantum rules stop applying, but because complex systems destroy phase information so quickly that quantum effects become invisible. Light exposes the boundary between quantum and classical reality. Now consider something even stranger.
Suppose we set up the double-slit experiment so that the decision to measure which path occurs after the photon has already passed the slits. In delayed choice experiments, this can be done using clever optical setups.
The photon passes the slits. Only afterward do we decide whether to measure which path information or to preserve interference. Astonishingly, the outcome matches the choice made later. If we preserve information, no interference appears. If we erase which path information, interference returns. It seems as if the photon's earlier behavior depended on a future decision. Feynman discouraged dramatic interpretations, but the implications are difficult to ignore. The quantum description does not define a fixed history independent of experimental arrangement. The experimental context shapes the phenomenon. It is not that the future changes the past. Rather, the theory refuses to describe events with classical definiteness in between measurements. Light travels from source to detector, but the story of how it did so is not part of physical reality unless measured. Between emission and absorption lies only probability amplitude. This raises profound questions about realism. Are particles real in the absence of observation? Or is what we call a particle simply a set of interaction possibilities? In quantum electrodynamics, light and electrons continuously exchange virtual photons, temporary disturbances in fields that cannot be observed directly, but influence measurable outcomes.
Virtual particles are not particles in the usual sense. They are bookkeeping devices in the mathematics, representations of intermediate states in the sum over histories.
But their effects are real. They shift atomic energy levels. They modify magnetic moments. They subtly alter the vacuum itself. The vacuum, in fact, is not empty. It seethes with fluctuating fields. Even in perfect emptiness, electromagnetic fields possess zero-point energy. Pairs of virtual particles flicker in and out of existence within the limits allowed by the uncertainty principle. Light traveling through vacuum interacts with this restless background. Empty space is an active participant. If classical intuition suggests that nothingness is blank and still, quantum field theory insists that nothingness vibrates. Feynman diagrams illustrate interactions as simple lines and vertices. But these diagrams represent integrals over countless possibilities. Every vertex corresponds to a probability amplitude. Every loop represents contributions from all allowable intermediate energy. When two electrons repel each other, we draw a diagram showing them exchanging a photon. But that photon is not a tiny billiard ball traveling neatly between them. It is a mathematical representation of interaction encoded in field equations. The electromagnetic force is light mediating between charges. So when light travels, it is not merely propagating energy. It is the mechanism by which charged particles influence each other. This is why light behaves differently from matter. It is both messenger and message. And unlike matter particles, photons have no rest mass. They cannot slow to rest. They cannot be localized in the same way. They exist only in motion. What happens if you attempt to confine a photon completely? If you trap light inside a mirrored cavity, it bounces back and forth, but its energy persists. The trapped electromagnetic field contributes to the system's effective mass. Energy has weight. Light confined can behave as if it has mass. But in free space, it cannot stand still. Now consider interference again. When two beams of light meet, they do not collide like particles. They superpose. Brightness increases where waves align. Darkness forms where they cancel. Yet if you lower intensity so that photons pass one by one, the interference pattern still builds up over time. Individual photons land at discrete points, but the distribution of many photons reveals wave behavior. Particle-like detection, wave-like probability. This duality is not a switch between two modes. It is a single mathematical framework producing two different observable aspects. Feynman's approach eliminates the wave-particle argument entirely. He replaces it with probability amplitudes. Light does not switch between being a wave and being a particle. It always behaves according to quantum amplitudes. Sometimes the amplitudes interfere in ways that resemble waves. Sometimes measurements produce localized events that resemble particles. The paradox is language, not mathematics. Still, there is something deeply unsettling about a universe built on probability.
If photons do not follow definite trajectories, then classical determinism is an approximation. On a fundamental level, we cannot predict exact outcomes, only probabilities.
Even with perfect knowledge of the present, the future contains intrinsic uncertainty. This is not due to ignorance. It is built into the structure of reality. Light exposes this limitation directly. Try predicting exactly where a single photon will land on a detection screen. Impossible. Only the probability distribution is calculable. But once detected, the photon leaves a permanent trace, a spot of energy transferred to matter, a measurable event. Spacetime arms actual. Potential becomes actual. In that transformation, something irreversible occurs. Information becomes fixed. Alternatives collapse into one realized outcome. Feynman cautioned against interpreting this collapse too literally, but the practical effect is undeniable. Quantum behavior gives way to classical record. The strangeness does not vanish at large scales, it becomes hidden under complexity. Everything around you is built from quantum processes of light and matter interacting. The solidity of objects, the color you perceive, the chemical bonds in your body, all arise from electromagnetic interactions mediated by photons. Without light, there would be no atoms as we know them. One, no stability of matter, no chemistry. Light is not just illumination, it is structure. It defines how electrons arrange around nuclei. It determines the allowed energy levels in atoms. It controls how molecules bond. Even the sensation of touch is electromagnetic repulsion at the atomic scale. Photons exchange between fields, preventing you from passing through the floor. You never truly touch anything. You experience light's force fields, resisting overlap. So when light travels, something strange happens. Not only in relativity's bending of time, not only in quantum interference, but in the deepest architecture of existence. Light operates beyond classical concepts of path, trajectory, and certainty. It is both mediator and mystery, where light meets the edge of reality. Now we reach the deepest layer of the mystery, because if light defines causality, if light builds atoms, if light shapes space-time, then one final question remains. What shapes light? Light seems fundamental. It has no rest mass. It cannot slow down. It travels at the universal speed limit. It mediates the electromagnetic force. It defines what events can influence others. But when we push physics toward extremes, immense gravity, microscopic scales, the earliest moments of the universe, light itself begins to face boundaries. And at those boundaries, something unsettling happens. The bending of light. Gravity. Einstein's general relativity tells us that mass and energy curve space-time. Planets curve it slightly. Stars curve it more. Black holes curve it so violently that space-time folds inward. And light, though massless, must follow the curves. In 1919, during a solar eclipse, astronomers observed starlight bending around the sun. The positions of stars appeared slightly shifted. Light was not traveling straight.
It was following curved space-time.
This was not because gravity pulls on light like it pulls on matter. Instead, gravity reshapes the geometry through which light moves. In curved space-time, the straightest possible path, called a geodesic, is itself curved. Light does not break its rules. It still moves locally at sea, but globally its route is distorted. Reality itself is not flat. Now imagine increasing gravity further. As a star collapses under its own weight, curvature intensifies. Eventually, escape velocity equals the speed of light. At that boundary, the event horizon, even light cannot climb out.
Rob, this is a black hole.
Inside the horizon, all possible future paths point inward. Light cannot move outward because space-time is curved so steeply that all geodesics lead deeper in.
The speed limit is preserved, but space-time gives no outward direction. This is important. Light is not overpowered. It is redirected. At the adjunct for the night, even at the edge of a black hole, light travels at sea, yet it cannot escape. And then something even stranger emerges.
I'm near a black hole.
As you approach a black hole, time dilation becomes extreme. To a distant observer, clocks near the horizon tick slower and slower. If you watched someone falling toward a black hole, they would appear to freeze near the horizon.
Their signals, light signals, become increasingly redshifted, losing energy, stretching into longer wavelengths.
Eventually they fade from view. But from the falling person's perspective, nothing extraordinary occurs at the horizon itself. They cross it in finite time. Two perspectives, two realities. This echoes Relativity's earlier lesson: time is not absolute. But now combine this with quantum mechanics. Because near a black hole's horizon, quantum fields cannot remain silent. Light from nothing. See, Stephen Hawking discovered that black holes are not completely black. Quantum fluctuations in the vacuum create particle-antiparticle pairs everywhere in space. Normally these pairs annihilate almost instantly. But near an event horizon, one particle may fall in while the other escapes. To a distant observer, this appears as radiation emitted by the black hole. Hawking radiation, light emerging from the edge of darkness. But where does its energy come from? From the black hole's mass. Over immense timescales, black holes evaporate. This is where our understanding fractures.
Because Hawking radiation seems thermal random. If information about what fell into the black hole is lost forever, then quantum mechanics' rule that information is preserved would be violated.
This is the black hole information paradox. Light once again sits at the boundary of our knowledge. Does information disappear? Is it subtly encoded in outgoing radiation? Except we still debate. Ziet u, zie the modenvaartig.
Aan differentiations work. That is beter found out in some contrast framepunkt. Og der er rent, jo en atom. So, handy what to like to
The equations of general relativity describe smooth spacetime. Quantum mechanics describes probabilistic amplitudes. And at that collision point, light, the mediator of forces, the carrier of information, cannot guide us further. The early universe, before light was free, now traveled backward in time. 13.8 billion years ago, the universe was hot and dense beyond imagination. In its earliest moments, temperatures were so extreme that atoms could not exist. Photons scattered constantly off charged particles in a dense plasma. Light could not travel freely. The universe was opaque. Only after about 380,000 years did expansion cool the cosmos enough for electrons and protons to combine into neutral atoms. At that moment, photons were released to travel largely unhindered. Those ancient photons still move today. We detect them as the cosmic microwave background, faint radiation filling the sky, a relic of the early universe. When we observe this radiation, we are seeing the oldest light in existence, light that has crossed nearly the entire age of the cosmos. It has experienced no time at all.
Minution and detection are adjacent events in the photon's frame, though billions of years apart in ours.
Does light experience anything? We must tread carefully here.
The photon has no valid rest frame in relativity. Strictly speaking, we cannot define the universe from its perspective.
But mathematically, as velocity approaches c, time dilation grows without bound. Length along the direction of travel contracts toward zero. This suggests something profound. For light, distance collapses. The journey disappears. What we call travel may be an emergent feature of observers moving slower than light. Perhaps light does not move through space in the way we imagine. Perhaps slower matter moves through space-time in a way that makes light appear to travel.
Light fundamental?
Modern physics suggests something radical. In quantum field theory, particles are not tiny objects, but excitations of underlying fields. The photon is an excitation of the electromagnetic field. Fields fill all of space. The photon is a ripple. But deeper theories suggest even space-time itself might not be fundamental. Some approaches to quantum gravity propose that space-time emerges from entanglement, from quantum information relationships more basic than geometry. If that is true, then light, which defines space-time's causal structure, may itself arise from something deeper. Not a wave, not a particle, but a manifestation of informational structure. This is speculative, yet hints exist.
The holographic principle suggests that information about a volume of space may be encoded on its boundary. Black hole entropy scales with surface area, not volume.
Information, not matter, may be primary, but light carries information. When you see a distant star, you gather data encoded in electromagnetic radiation. When atoms bond, it is information exchanged through photons. When your brain processes vision, it is decoding patterns of light.
Light transmits structure across the universe.
But if space-time emerges from more fundamental quantum relationships, then light's role might not be foundational, but derivative. A surface phenomenon of deeper rules. The final limit. We have never accelerated anything with mass to light speed. To do so would require infinite energy. This suggests light speed is not just a technological barrier, but a structural one. The universe is built-in ceiling. You cannot send information faster than light. You cannot observe outside your light cone. You cannot see beyond the cosmic horizon if expansion outpaces light's ability to reach you. There are regions of the universe permanently inaccessible, not hidden by distance alone, but by time and geometry. Light defines the boundary of what can ever be known. And yet quantum entanglement challenges this boundary. Two particles prepared together can exhibit correlations instantly across vast distances. Measurements on one correlate with measurements on the other, faster than light, could travel. But this does not transmit usable information faster than C causality survives. Still, it hints that underneath light's structure, deeper connections exist. Connections not limited by space-time in the usual sense. Perhaps space-time itself is emergent from entanglement networks. If so, light is both guide and mask, revealing structure while hiding its origin.
Something strange is always happening.
We began with a simple question. What happens when light travels? We discovered that space contracts. Light paths multiply into probabilities. Vacuum fluctuates. Black holes glow faintly. The early universe becomes visible. Causality defines boundaries. Light is not merely something inside the universe. It is woven into the rules that make a universe possible. Without light, no structure holds. Without light speed, no causality exists. Without photons, no atoms bind. And yet, at the deepest level, we are not certain whether light is the foundation or a surface ripple of something more abstract. Feynman once admitted that nature's behavior is absurd from the standpoint of common sense. Literally see you.
Light exposes that absurdity directly.
It travels at a speed that does not adjust.
It takes all paths, yet arrives at one place.
It cannot be at rest without slowing.